about all the great results from our recent Phobos Deimos workshop. For those of you who are here, thank you for that. It was truly fantastic, and we got a lot of really good feedback. So look forward to hearing the results. Thanks, Pascal.
Okay, good afternoon. Thank you for staying. Yes, so we did have a really good conference. The very first international conference was in 2007. This was long before the launch of Phobos Grunt. Then we had a second one in 2011, again held at Ames, where it was on the eve almost of the launch of Phobos Grunt. And as you know, Phobos Grunt was this Russian mission to land and return samples from Phobos. And of course, it did not have a happy end. And so following that, there was sort of a lull of about 5 years. And then just yesterday and the day before, we had our third international conference. And it was sort of time to look forward, to look at the future. And so Greg Schmidt and I were co-conveners of this conference, but there were lots of people behind it to make it happen. And I just wanted to express my thanks to everybody for participating and making it happen. So the conference had plenary sessions only. We had 2 science sessions, one dedicated to robotic reconnaissance, robotic missions, new missions, and recent results from ongoing missions, or even past missions. And then we had a session dedicated to human exploration planning, which was also very exciting. And so I'm just going to give you a completely biased, selected overview, sort of a sampling of what I captured and had time to sort of write up for this quick overview, since the conference ended just last night. And most people who participated are not mentioned in this overview, and also those who are mentioned, I'm sure I'm not doing them justice. So, but nevertheless, let's move forward. Next slide. Oh, do I control this? All right. So one of the important and sort of overbearing issue on the science sessions was the origin of Phobos and Deimos. It's still unresolved. We are now close to 5 decades after the first robotic mission to Mars, and we still do not know what the moons of Mars are, let alone how they got there, or what they're like on the inside. There's 3 prevailing hypotheses. The first one, maybe historically, is that they're captured small bodies, and notice that I'm not saying captured asteroids or comets, I'm just saying small bodies from the outer main belt or beyond. The second hypothesis is that they're remnants of Mars's formation. And incidentally, in that bin, one would put not just accretionary disk material, but also contributions from the inner solar system, things that might be even captured small bodies that are not from the outer main belt or beyond, but sort of from the inner main belt. And then in the third category, we have this more recent idea that was proposed by Bob Craddock in 2011 and has now given rise to a lot of work and modeling. It's the idea that Phobos and Deimos might be reaccreted Mars impact ejecta. I should also say quickly that it's not even assumed that Phobos and Deimos have the same origin. They're actually very different bodies. And also, each one of these sort of hypotheses has actually several fatal flaws unless you do modeling, in which case you can make anything happen. But the captured small body issue really is the fact that Phobos and Deimos, for example, are on equatorial and circular orbits. And if they were captured small bodies, you would expect them to be on elliptical and highly eccentric and inclined orbits. And it's very difficult to disincline an orbit if these bodies are rigid, at least, et cetera, et cetera. So you have to resort to sort of workarounds to make any one of these work out. And so we've had a breakthrough actually presented at our conference by Pascal Rosenblatt and his teammates. So Pascal has done some modeling on the giant impact hypothesis The big challenge in this scenario is that if you form Phobos and Deimos as a result of accreted bodies in a debris ring that results from a giant impact, they tend to decay from their presumed close to synchronous orbit position into Mars too quickly. So the decay happens much over timescales that are much shorter than the age of the planet, and so actually that's a problem that's actually common to all three hypotheses. But the modeling that was done here creates a giant impact and an accretion disk that allows for the formation at an early stage of a very large moon. This very large moon no longer exists. You can see that in step 3 and 4. You form this large moon that's closest to Mars. And Phobos and Deimos are sort of forming by accretion outside of this large moon. And somehow the presence of the large moon, first of all, allows Phobos and Deimos to accrete, and second, retards their tidal decay into Mars until the large moon itself falls towards Mars, breaks up presumably, and then crashes onto Mars. And at that point on, Phobos and Deimos begin their gentle migration inwards for Phobos, outwards for Deimos, and they are where they are found today. And in this particular scenario, it works, and so we could say that in this is providing one solution to the problem. Now, there's a lot more work that's going on. Julian Selman, for example, has been looking at what happens to giant impact disks by varying the impact parameters with Mars. He did a parametric study of the distribution of mass on the outer part of the disk to see whether or not you could form Phobos and Deimos near the synchronous orbit. He has models that show you can form up to 5 moons, but so far they're larger than Phobos and Deimos are today, so there's more work that's going on there. Ngoc Trong from Vietnam presented a nice poster. He reviewed the water content in the Australasian tektite. So these are the terrestrial tektites. These are terrestrial impact ejecta that fell back after suborbital trajectories onto the Earth. And he shows that even the highest energy australites, which were heated to 2,000 degrees centigrade, were ejected at speeds between 6 and 11 kilometers per second, would still retain original water up to a level of about 0.001 weight percent in water. So this suggests that large impacts into a water-rich body, and possibly Mars, may yield non-escaping orbital disk debris that would contain water as well. So in other words, these giant impact events don't necessarily boil off all the water that's in your target material. Then we move on to the surface. We've had several talks about the surface of Phobos in particular. So Eric Asbog has been looking at the grooves on Phobos, and he tells us that the groove networks are consistent with fracturing by tidal stresses in a very weak, thick, powdery, elastic, regolithic crust. Okay, so the new way of thinking about the interior of Phobos, essentially, is that you have a highly porous, maybe not even consolidated, deep interior, and things are sort of held together in some sense almost by a thickish regolith crust that's somewhat more compacted and has a little bit of cohesion, but is nevertheless very powdery. Okay, so think of I'm calling that caking myself, but it's what you see in nature when you're dealing with drying clays, for example. They sort of cake up, so you have a rigid top surface of a very powdery material, and then things that are more rubbly underneath. So it's an interesting geophysical model because it has also been successfully tested in other modeling of tidal evolution for Phobos to create the networks of grooves, etc. Bill Botke has been looking at crater counting. So Bill tells us that the largest craters on Phobos and Deimos are consistent with a Borealis basin age for the two bodies. So in other words, if they were that old, they would not necessarily have more large craters than they have right now. And so this suggests that they were never disrupted. Ramsley and Head gave a nice paper on the modeling of the fate of impact ejecta in Mars orbit, and they show that when you toss ejecta forward, for example, from Stickney, that 90% of the impact ejecta from Phobos will return to Phobos. So that's good to know. In case you lose something, chances are it will come back if you are on Phobos. But Stickney is therefore has been sort of impacted by its own secondary. Well, it carries impact craters that are secondaries of its own impact ejecta. So it's not straightforward to date Stickney just by counting craters alone. Dan Shears gave a nice paper on the dynamic environment on and about Phobos, so showing us the subtleties of the topography versus the gravity and how things move around or would not on Phobos. And he also introduced this interesting concept of a speed limit on Phobos, which is a speed you want to always avoid in order not to escape. All right, we had several really good contributions in, I'm lumping this together into the dust and particles and fields science topics. So first of all, regarding dust and regolith, there were quite a few discussions during and between talks on Martian ejecta in the regolith of Phobos and also asteroidal contamination. I'm always reminded when I discuss this of numbers that were given to me by Brett Gladman a few years ago, that for every piece of Mars that you might find in the regolith of Phobos, you should expect to find 30 times more asteroidal debris as well. So sifting through Phobos regolith to look for pieces of Mars will require, well, actually should yield a lot of asteroidal finds as well. Micah Schabel, who is finishing his PhD and is looking for a postdoctoral position, gave a very nice paper on neutral gas and ion sputtering on Phobos, and is showing us that the expected fluxes should be measurable by a mass spectrometer that would be flying by Phobos. So this is sort of an interesting result, and there's more modeling to be done, and I think that's something he hopes to do in a good postdoc. The plasma environment is also shown to be very dynamic. Andrew Poppy showed us that through some early results with MAVEN. And then Mihaly Horanyi showed a really nice, showed some nice results of modeling of dust transfer between the moons of Mars, and in particular from Deimos to Phobos. So dust is kicked off of Phobos and Deimos by micrometeoric bombardment mainly. And it experiences different fates depending on the particle size, but some of the material drifts inward essentially and catches up with the trailing side of Phobos, and over time you get a map like this, where the reds and the yellow represent high levels of deposition of Deimos dust onto Phobos, and where the gray and purple areas are the areas that collect less dust from Phobos and Deimos. And the bottom line is that the influx of material onto the trailing side of Phobos is of order 10 centimeters per million year. Okay, so a meter per 10 million years. So there's potentially a lot of material from Deimos that's accumulating on the backside on the trailing side of Phobos. And this is really interesting because, first of all, it feeds into this notion that Phobos, which has two spectral units, a dominating surface-wise redder unit, spectrally redder unit, compared to a less exposed bluer unit. But this redder unit, even though it's dominating the surface of Phobos, could be an acquired veneer of material from Deimos. So most of Phobos basically might be showing you just what Deimos is shedding. And so you might want to, if you want to sample Phobos properly, go to places that at the very least will give you access to both types of terrain units. But 2 minutes, okay, yeah, sure. So in any case, I'm getting carried away. A really exciting result. Now, of course, we don't know how, once the material has landed on the trailing side, how it might also get eroded and re-injected into the Martian system for further drifting. So this is a map of the influx. So we've had discussions on robotic reconnaissance. Hendrix gave us some interesting new data, or reprocessed data from the Mariner 9 ultraviolet spectrometer with a nice blue absorption at 3,500 angstroms. That's consistent with organics, but of course even she recognizes that it may not make sense, so we aren't quite sure what it's due to. Conrad Wilner from DLR has informed us that Mars Express will continue its flybys of Phobos. The 2018 campaign is being planned. They're applying for an extension to 2020 as well. And in 2018, we should be imaging the trailing side of Phobos, which is not well imaged. Mike Chaffin also gave us some nice UV results from MAVEN of the trailing side of Phobos, and is showing us that it's consistent with increased weathering on this side or a compositional difference. So it might be what Mihaly is dumping onto the backside of Phobos. There were discussions of two important upcoming missions. Japan's Martian Moons Exploration Mission, which is really moving forward nicely. The launch date is planned so far for 2022. Sample return by 2028 to 2030. A robotic arm will core and extract samples. We expect to bring back 10 grams of Phobos regolith acquired over a depth of about 10 centimeters from the surface. The duration of the lander at the surface was, I'm not 100% sure this is correct, but I was surprised, so I took that down. It was 1 to 2 hours. And the payload is already more or less defined. You'll have a visible camera from JAXA, a near-infrared spectrometer from France, a gamma ray with 2Ms, a neutron spectrometer to be contributed by the US, and a surface package of about 10 kilos, which hasn't been defined yet. On the ESA side, Alastair Wayman just gave you a quick summary of what's being planned. So I'll just say that in contrast to the MMX mission, it might launch a little bit later. The launch, is not 2005 here, it's 2025. Sample acquisition would be in 2028. The spacecraft would stay 100 Phobos days on the surface, so that's a little over a month on Phobos. And the samples would get back to the Earth in August of 2030. Okay. And we'd be bringing back about 100 grams from Phobos. All right, so there were some input from NASA headquarters. So Jim Green told us that Phobos and Deimos are very important. We expect to find pieces of Mars in their regolith. He expects the salmon call to move forward. Okay, so that should be happening in August, we were told. And then the Mars 2022 orbiter should also include investigations of Phobos and Deimos that will be opportunistic. Tom Statler, who was here too from headquarters, invited us to really plan for not just acquiring the samples from Phobos and Deimos in collaboration with JAXA, but also to curate the samples. And then Greg Schmidt here has proposed the formation of a new survey focus group on Phobos and Deimos. A few meeting facts: 50 abstracts submitted, 200 plus participants, 150 on-site attendees, 20 students. Tushar Mittal from University of California, Berkeley, got the Asaph Hall Best Student Paper Award on a paper on the fate of Phobos, and so we'll break up, turn into a ring, and then fall onto Mars eventually. We had a space art exhibit over the 2 days. It was nicely attended, and it featured, in particular, this really nice painting by Chesley Bonsdale, which is a NASA Ames-owned piece of history. All right, thank you.
We do have a couple moments for questions, and while I wait for hands to go up, I would like to reiterate the fact that the Phobos Deimos talks were archived on they will be archived on the Phobos Deimos website if they're not already. So if you unfortunately missed that workshop, then please go to the website and check them all out.
I'm told the abstract book, along with each individual presentation, poster, or PowerPoint, will be downloadable starting end of next week.
Any other questions for Pascal? Okay, I think we'll go ahead and move on into the light.